The cosmos is a book with most of its pages glued shut. We can see the starry cover, but entire chapters are forever sealed away. This is a tour of the 25 most enigmatic regions of the universe we can never explore. You will see the ultimate boundaries of human knowledge, places where physics itself breaks down and distance becomes an eternal prison. What waits inside a black hole's core, and what lurks beyond the edge of everything we can see. The answers redefine reality itself. Are you ready to confront the limits of our cosmic reach? The first sealed chapter lies at the very end of a black hole's gravitational embrace. Past the point of no return, the event horizon, space and time trade places. Falling inward, you could no more stop your descent toward the center than you could travel back in time. And at that center awaits the singularity. This is not an object you could touch or see. It is a point where the fabric of space-time, warped beyond all measure by the collapsed star's immense mass, curves into an infinite pinch. All the equations of general relativity scream in protest, yielding answers of infinity, infinite density, infinite curvature. The known laws of physics do not simply fail here, they vanish entirely, leaving behind a blank space on the cosmic map labeled "Here be dragons." Within that mathematical void, speculation runs wild. Some theories suggest the singularity might be a gateway, a tunnel through the hyper-stretched geometry of spacetime itself, potentially connecting to another region of our universe or even a different cosmos entirely, a wormhole. Others propose it is a boundary, the true edge of reality as we understand it. But these are stories we can never verify. Any probe, any information, any whisper of what happens at the singularity is trapped forever behind the event horizon's one-way wall. It is the ultimate locked room mystery, with the key itself swallowed by the darkness. This region represents more than a place we cannot visit. It is a fundamental limit on human knowledge, a permanent question mark inscribed into the universe's deepest laws. But the singularity is not the only locked door within a black hole. There is another, more profound mystery wrapped around its very surface, a paradox that threatens to unravel our understanding of reality itself. This is the black hole information paradox. To understand it, we must start with a surprising discovery by Stephen Hawking. He realized that black holes are not completely black. Due to strange quantum effects happening right at the edge of the event horizon, they slowly leak a faint glow of particles, now called Hawking radiation. Over eons, this radiation causes the black hole to evaporate, shrinking until it eventually vanishes, and here lies the terrible problem. According to the bedrock principle of quantum mechanics, information can never be truly destroyed. Every bit of data about what fell into the black hole, the specific arrangement of atoms that made up a star, a planet, or a hypothetical spaceship, must be preserved in some form. But if the black hole evaporates into a featureless cloud of Hawking radiation, that information seems to be erased from the universe forever. It is a cosmic contradiction, a war between the law of gravity that creates the black hole and the law of quantum mechanics that governs its demise. To resolve this paradox, physicists have proposed ideas so strange they sound like science fiction. One of the most radical is the firewall hypothesis. It suggests that the event horizon is not a smooth, empty gateway. Instead, it might be a seething wall of unimaginably high energy particles, a literal firewall of pure chaos. Anything crossing it would be instantly and completely incinerated into its most fundamental particles. This solves the information paradox in a brutal way. The information of the falling object is not lost inside the black hole, it is smeared across this violent horizon. But it creates a new, shocking implication. The gentle fall through the event horizon predicted by Einstein's relativity, where you might not even notice crossing the point of no return, would be a fantasy. The interior of the black hole, that mysterious landscape leading to the singularity, becomes not just physically inaccessible but conceptually forbidden. You could not explore it even in principle, because to reach it, you would have to cease to exist as a coherent entity. This means one of our 25 enigmatic regions is doubly sealed, barred by infinite gravity at its core, and potentially guarded by a wall of fire at its door. The universe seems to be telling us that some rooms are not meant for visitors, and their secrets are kept safe by the very laws that govern existence. Yet the black hole's firewall presents a paradox of proximity, a mystery pressed right up against the event horizon. Our second sealed region exists at the opposite extreme of scale, a boundary not of gravity but of light and time itself. This is the cosmic horizon, the absolute edge of everything we can ever see. Picture the universe not as a static stage but as an inflating balloon. Galaxies are like dots on its surface, constantly moving apart as the balloon expands. The light from those galaxies is like tiny ants crawling across the stretching surface toward us. Now consider a galaxy so tremendously far away that the space between us is expanding faster than the speed of light. This is not science fiction. It is a direct consequence of the universe's accelerating expansion. The ant of light from that galaxy, no matter how tirelessly it crawls, is on a treadmill set to an ever-increasing speed. It will simply never reach us. The sphere defined by the most distant light that has managed to arrive after traveling for 13.8 billion years, that is our cosmic horizon. Everything within it is our observable universe. Everything beyond it is, and always will be, utterly invisible and inaccessible. This horizon is not a physical wall you could crash into. It is a fundamental limit of information, a curtain drawn by the expansion of space itself. We are forever at the center of our own observable bubble, and the vast majority of the cosmos, perhaps an infinite expanse of other galaxies, alien structures, and unimaginable wonders, lies eternally outside our view. Their stories began with the Big Bang, just as ours did, but the narrative of their existence is written in light that will never arrive. They are causally disconnected from our pocket of reality, forever receding into a darkness more complete than any void. We can infer they are there, but we can never gather a single photon of evidence, making the cosmos beyond the horizon the ultimate example of a place we are destined to only wonder about. But our cosmic isolation is defined by distance, by the stretching of space itself. The next sealed region is one of impossible proximity, a world of matter crushed into forms so extreme they defy every intuition. Deep within the corpse of a massive star, after a supernova has blasted its outer layers into a brilliant nebula, a remnant core can collapse into a neutron star. This is a city-sized object, barely 20 kilometers across, yet containing more mass than our Sun. The gravity at its surface is so intense that if you could drop a marshmallow from just 1 meter above, it would impact with the force of a nuclear bomb. But the true mystery, the place we can never visit, lies beneath that unimaginable surface in the interior of a neutron star. We can model it, we can theorize, but we can never, ever see inside. Think of a neutron star as an onion of impossibility. Its thin, solid crust is a lattice of iron nuclei, packed so tightly by gravity that it becomes the strongest material in the universe, 1 billion times stronger than steel. Just a single teaspoon of this crust material would weigh billions of tons on Earth. But as we descend, pressure mounts to levels that make the core of our Sun seem like a vacuum. Here, the atomic nuclei themselves are squeezed until they lose their identity. They merge and deform into long tubes and sheets, a phase physicists call nuclear poster, a bizarre state of matter that exists only under these cosmic pressures. This strange substance is likely the strongest part of the star, and it might even create mountains on the surface no taller than a few millimeters, yet massive enough to create ripples in spacetime itself. But the deepest core is where our physics truly breaks down. Under pressures 100 trillion times greater than Earth's atmosphere, protons and electrons are forced together to become neutrons, giving the star its name. Yet even neutrons might not be the final stage. Some theories suggest the very neutrons themselves might dissolve into a swirling soup of their constituent particles, free quarks, creating a new state of matter called quark-gluon plasma. Others speculate that a strange form of matter made of up, down, and strange quarks could form a stable, hyper-dense core. This strange matter would be the most perfect, stable substance in existence. If it exists, a single drop could convert any normal matter it touches into more strange matter, a theoretical doomsday substance. Is the heart of every neutron star a seething ocean of free quarks, or a crystalline lump of this apocalyptic material? We have no way to know. Our most powerful particle colliders can only create fleeting hints of quark-gluon plasma for microscopic fractions of a second. We cannot recreate the sustained, crushing embrace of a neutron star's core. It is a laboratory of extremes forever closed to us, its secrets locked inside an object so dense that light itself bends into a tight circle around it. We see these stars as pulsars, flashing cosmic lighthouses, but their true nature, the reality of matter under ultimate pressure, remains one of the universe's most profound and inaccessible puzzles. The heart of a neutron star is a vault sealed by gravity's ultimate force. Yet there is another era of cosmic history, not hidden by density but by the very nature of light itself. This is the universe's first 380,000 years, a time before stars, before galaxies, before atoms as we know them. In that primordial age, the cosmos was not a dark void sprinkled with lights. It was a searing, brilliant fog, a nearly uniform soup of fundamental particles, protons, electrons, and photons of light, all bouncing and colliding in a dense, scorching plasma. In such a state, light was not free. An electron with its negative charge would immediately capture any photon trying to escape, scattering it in a new direction. The universe was utterly opaque, a glowing prison where light could not travel in a straight line for more than a tiny fraction of a second. For us, this means a permanent observational blackout. We have no telescope, no instrument that can peer back past this wall of plasma. It is our ultimate blind spot. Everything that happened in that first long cosmic childhood, from the first second to that 380,000th year, is hidden from direct view. Within that opaque glow, the universe performed its most critical magic. The energy of the Big Bang cooled just enough for electrons to finally be captured by protons, forming the first hydrogen atoms. This moment, called recombination, was the universe clearing its throat. With electrons now bound into atoms, the constant scattering stopped. Photons were suddenly set free, streaming across the cosmos in all directions. That first burst of liberated light is what we detect today as the cosmic microwave background, the oldest picture we have. But it is a picture of the surface of that fog the moment it cleared. It tells us nothing of what happened inside the fog itself. How did the first structures begin to clump? What were the precise seeds that would one day grow into galaxies? Were there exotic particles, now long vanished, that shaped this early soup? We are left with only theoretical models like cosmic inflation, the idea of a sudden, faster-than-light expansion in the universe's first fraction of a second, to explain the patterns we see imprinted on that ancient light. The era before the background radiation is a sealed chapter of cosmic evolution. Its narrative written in a language of plasma we can no longer decipher, the formative years of everything lost in the glare of creation's first dawn. That ancient light reveals the universe's first structures, but it cannot show us the invisible glue that holds them together. We know our galaxy, the Milky Way, is not just a disk of stars. It is embedded within a vast spherical cloud of something we cannot see, touch, or feel. This is the dark matter halo, a ghostly realm that permeates every corner of our galaxy and yet remains utterly unexplorable. Dark matter is the universe's greatest sleight of hand. We know it is there because we can watch its gravitational performance. Stars at the edges of galaxies orbit far too quickly to be held by the gravity of the visible stars alone. Entire clusters of galaxies bend light from objects behind them, a phenomenon called gravitational lensing, with a strength that demands the presence of far more mass than we can account for. This invisible mass, this dark matter, forms immense halos around galaxies, providing the gravitational scaffolding upon which the luminous universe is built. We can map the rough shape and size of this halo by its effects, but that is like mapping a mountain by the wind patterns around it. The mountain itself, the true substance of the dark matter halo, is a complete mystery. We are passing through it right now. As you listen to this, trillions of dark matter particles are likely streaming through your body every second, leaving not a trace, interacting with nothing. This is the core of the enigma. Whatever dark matter is, it does not interact with light. It does not emit, absorb, or reflect photons. It also seems to ignore the electromagnetic force that governs chemistry and lets you touch solid objects. It interacts, as far as we can tell, only through gravity and possibly the weak nuclear force. This makes it not just dark, but nearly perfectly transparent and frictionless to our entire reality. Theorists have proposed candidates for what these ghostly particles could be. WIMP, or weakly interacting massive particles, are heavy, sluggish entities that could have been forged in the early universe's heat. Actions are hypothetical ultralight particles, trillions of times lighter than an electron, that could flow through the cosmos like a subtle wave, but these are just names for our ignorance. The interiors of these vast halos, regions millions of light years across, are filled with a substance whose fundamental nature is a blank. We cannot send a probe into the halo to sample it. We cannot build a detector that catches it easily. Our entire galaxy spins within this silent, unseen ocean, and we have no way to dive in and learn its composition. It is a frontier defined by absence, a territory we inhabit but can never truly know, making the dark matter halo one of the most profound and frustratingly intangible regions on our list of cosmic no-go zones. Our galaxy's silent heart is not a place of gentle starlight but a monster's lair. At the very center of the Milky Way, 26,000 light-years away, lies Sagittarius, a star, a supermassive black hole with the weight of over 4 million suns. This is the gravitational anchor of our entire spiral dance, a cosmic plug hole around which everything we know slowly swirls. While its smaller stellar cousins offer terrifying endpoints, a supermassive black hole like this presents a different kind of mystery, one of scale and subtle, inescapable power. The region around its event horizon is a place of profound and deceptive calm, a realm of physics so extreme it creates a prison not just of space but of time itself. Picture an astronaut on a doomed mission, bravely piloting a ship toward that ultimate boundary. To us, watching from a safe distance with powerful telescopes, a bizarre scene would unfold. As the ship approaches the event horizon, the intense gravitational field would cause a dramatic effect called time dilation. Time for the astronaut would flow normally, but from our perspective, their clock would tick slower and slower. Their approach would seem to decelerate, their movements becoming a glacial crawl. At the very threshold of the horizon, they would appear to freeze completely, a ghostly image stamped onto the edge of darkness, red shifted into oblivion. They would never, from our point of view, actually cross. This is the universe's most cruel illusion, a farewell stretched into eternity. For the astronaut, of course, the crossing is horrifically swift and one-way. There is no fanfare, no sudden jolt. They pass the point where the inward flow of space itself exceeds the speed of light. Not even light, the universe's ultimate speedster, can fight that current to bring news back out. The ship is swept inward, and the outside universe shrinks to a bright, shrinking disk of light above before winking out forever. But the moments just before that final silence are a theater of cosmic distortions we can only simulate. The difference in gravitational pull between your head and your feet, a force called spaghettification, would be powerful enough to stretch any object into a strand of atoms. The light from stars behind you would be bent into impossible rings and arcs, warping the entire cosmos into a funhouse mirror wrapped around a pit of blackness. This immediate vicinity, this last mile before the point of no return, is a landscape of mathematical certainty and experiential impossibility. We can calculate its properties with exquisite precision, yet we can never send a probe to confirm them, for any data it gathered would be as lost as the probe itself. Sagittarius, a star, is our closest supermassive guardian of the unknown, a dark titan whose front porch is a place of frozen time and certain doom, making it a permanent monument to the limits of human exploration. Sagittarius, a star, represents a boundary of cosmic scale, but our next sealed region exists within our own celestial backyard, a frontier so vast it makes the distance to Pluto seem like a stroll down the street. This is the Oort cloud, a hypothetical shell of icy debris believed to encase our entire solar system like a thin, distant fog. Its existence is inferred from the long, looping orbits of certain comets, those ancient wanderers that take thousands or even millions of years to complete a single journey around the sun. These comets must come from somewhere, a vast reservoir of frozen material left over from the solar system's chaotic birth. That reservoir is the Oort cloud. To grasp its scale, consider this: the Voyager 1 probe, launched in 1977, and now the most distant human-made object, has traveled for over 4 decades. It has only just left the influence of the sun's constant particle wind, a bubble called the heliosphere. To reach the inner edge of the theorized Oort cloud, Voyager would need to keep flying for another 300 years. And to pass completely through this shell and into true interstellar space, that journey would take a staggering 30,000 years. This places the cloud's outer boundary nearly a light year from the sun, halfway to the nearest star. Within this unimaginable volume, the objects of the Oort cloud are not packed together. They are lonely icebergs adrift in a cosmic ocean darker than any night. They reflect almost no sunlight, and they are so far apart that a traveler passing through might go for millions of kilometers without ever glimpsing one. This combination of immense distance, profound darkness, and incredible isolation makes the Oort cloud nearly impossible to observe directly. It is a ghostly silhouette we deduce from the rare comets that are gravitationally nudged from their frozen slumber and sent falling inward toward the sun. Each of these icy planetesimals is a frozen time capsule, a pristine sample of the original material that coalesced to form our planets over 4.5 billion years ago. Studying one up close would be like reading the first page of our solar system's history book, yet this makes the Oort cloud a deeply frustrating enigma. It is an archive containing the answers to our origins, sitting right on our cosmic doorstep, but locked inside a vault we cannot open. Even with our most ambitious propulsion ideas, a dedicated probe would take centuries just to arrive. The cloud is not guarded by event horizons or walls of fire, but by the simple, cold mathematics of distance and time. It is a frontier we can dream of, one we know must be there, but one that will almost certainly remain untouched by human technology for thousands of generations to come. We are surrounded by a frozen memory of our own creation, forever just out of reach. The Oort cloud is a frozen borderland we can at least point to on a map. But our solar system occasionally ejects its own children, casting them into a deeper exile with no map at all. These are rogue planets, worlds torn from their parent star's gravity during the chaotic dance of planetary formation. They do not orbit any sun. They are solitary wanderers drifting through the interstellar void on random, lonely trajectories. To stand on the surface of such a world would be to experience the ultimate definition of night. There is no sunrise, no sunset, only an eternal, star-studded blackness above a frozen, desolate landscape. With no nearby star to provide warmth, temperatures on the surface would plummet to just a few degrees above absolute zero, the coldest possible temperature in the universe. Any atmosphere the planet once possessed would have long ago frozen solid, falling as a perpetual snow of nitrogen, oxygen, or methane, creating a crust of exotic ices harder than granite. The silence would be absolute, broken only by the occasional groan of the planet's own shifting crust. Yet within this seemingly dead husk, a tantalizing possibility flickers. Many of these rogue worlds, especially larger ones akin to Jupiter or Neptune, could retain immense internal heat from their violent formation. This geothermal warmth might be enough to maintain vast global oceans of liquid water trapped beneath miles of solid ice. Imagine an abyss darker than the deepest ocean trench on Earth, under an ice shell thicker than our continents, warmed from below by the planet's own slow cooling heart. This presents a staggering thought. Life, as we understand it, requires liquid water and an energy source. Around a star, that energy is sunlight. In a sunless abyss, life would have to rely entirely on chemical or geothermal energy, much like the ecosystems huddled around hydrothermal vents on our own ocean floor. A rogue planet's subsurface ocean could be a self-contained, isolated biosphere, a sealed bottle adrift in the galaxy, its inhabitants utterly unaware that stars or a universe of light even exist. Their entire cosmos would be the dark water and the warmth from below. Reaching such a place, however, is a challenge that borders on the impossible. First, we must find one. Rogue planets emit no light of their own and are exceptionally dim, only detectable through rare microlensing events when their gravity briefly magnifies the light of a distant background star. Second, we must reach it. With no star to sail toward, no solar system as a destination, a mission would be a shot into the absolute dark. A probe would have to carry all its energy for the entire journey, with no hope of solar panels, on a voyage that could last tens of thousands of years. Even if we could somehow get there, landing on that frozen, airless surface would be a descent into a permanent alien winter. We might drill through the ice seeking that hidden ocean, but the technology to do so across such distances is pure fantasy. The surface of a rogue planet is therefore a double prison. It is a physical location of extreme cold and darkness we are unlikely to ever touch, and it is a veil over a potential secret, a hidden, living ocean whose story would rewrite our understanding of life's tenacity. That story is written in the dark on a page we cannot turn. Rogue planets drift in the cold interstellar night, but a world of profound darkness and potential life exists much closer to home, orbiting a brilliant giant. Jupiter's moon Europa gleams like a cracked marble, its surface a smooth shell of water ice crisscrossed by deep, rusty fractures. This serene exterior hides a secret that reshapes our search for life in the cosmos. Beneath that ice, perhaps only 10 or 15 miles deep, sloshes a global saltwater ocean containing more than twice the liquid water found on all of Earth. This is not a small sea, but a planet-wide abyss sealed under a frozen sky. The ice shell itself is a dynamic world, with giant plates shifting and churning, possibly allowing chemicals from the surface to percolate down and nutrients from below to rise up. But the true mystery, the place we desperately wish to explore, lies at the very bottom of that alien sea. On Earth, the deepest, darkest parts of our oceans are not barren. Around hydrothermal vents, where superheated, mineral-rich water erupts from the planet's crust, entire ecosystems thrive without a single photon of sunlight. They are powered by chemosynthesis, life drawing energy from chemicals rather than light. Europa's rocky seafloor, warmed by the immense tidal forces of Jupiter's gravity squeezing the moon's interior, is almost certain to host similar vents. These could be oases in the dark, providing the energy and chemistry needed to sustain life. The potential is staggering. Microbial life, or perhaps something far more complex, could be swimming in those pitch-black waters right now. Yet, reaching that ocean floor is a challenge that makes landing on Mars look simple. First, a spacecraft must land on the unstable, fractured ice, avoiding geysers and treacherous terrain. Then, it must deploy a probe capable of melting or drilling through up to 15 miles of solid ice, a task never before attempted. The ice is not uniform. It likely contains pockets of slush, harder crystalline layers, and embedded rocks. The drill would need to operate autonomously for months or even years, all while maintaining a sterile pathway to prevent earthly microbes from contaminating this pristine environment, a paramount ethical concern. And finally, once through the ice, a submersible would need to navigate an utterly dark, high-pressure ocean, map an unknown seafloor, and find a vent site, all while communicating back to the surface through that miles-thick ice cap. Each step is a monumental engineering hurdle. We can orbit Europa and study its surface. We may one day land a craft to sample the icy material that has welled up from below. But the ocean floor itself, that dark frontier where alien life may truly exist, remains a realm of profound speculation. It is a world within a world, a hidden abyss we can infer, model, and dream about, but one whose deepest secrets are locked away under a permanent, frozen sky. Europa's hidden ocean is sealed beneath a frozen crust, a physical barrier of immense scale. But there exists a frontier of a completely different nature, one where the barriers are not made of ice or distance, but of the fundamental grain of reality itself. This is the quantum foam of space-time. To understand this, we must shrink our perspective to an almost incomprehensible degree. Forget planets and stars. Forget atoms and even atomic nuclei. We must journey down to the Planck scale, a realm so tiny that numbers fail to convey its size. If you enlarged a single atom to the size of our entire solar system, the Planck length would be roughly the height of an average tree on Earth. At this unimaginably minute scale, the smooth, continuous fabric of spacetime that Einstein described begins to break down. According to quantum theory, empty space is never truly empty. It is a seething, chaotic froth, alive with violent energy fluctuations. Think of the calm surface of a pond on a windless day. From a distance, it appears perfectly flat and glassy. But if you could shrink down to the size of a water molecule, you would see a frantic, churning chaos. That is the quantum foam. Here, the very concepts of here and now lose their meaning. Tiny wormholes, bridges connecting separate points in space, are thought to blink into and out of existence in less than a Planck instant. Virtual particle pairs, consisting of a particle and its antiparticle, spontaneously erupt from the vacuum, borrowing energy from nowhere before annihilating each other and returning it, all within a time span so short it defies measurement. This is the basement level of the universe, the fundamental substrate from which everything, including the dimensions of space and time themselves, is thought to emerge. Yet this is a basement we can never visit. The energy required to probe such tiny distances is beyond colossal. It would require a particle accelerator larger than our galaxy, or energies concentrated into a point so small they would instantly collapse into a microscopic black hole. Our entire universe of stars, galaxies, and planets is built upon this frenetic, foamy foundation, but we are forever too large, too slow, and too clumsy to perceive it directly. It is the ultimate theoretical landscape, the place where the two great pillars of modern physics, the cosmic gravity of Einstein and the probabilistic weirdness of quantum mechanics, must finally shake hands and unite into a theory of quantum gravity. Until that day, the quantum foam remains a magnificent deduction, a logical necessity written in the mathematics of our most advanced theories, yet a layer of reality forever hidden from direct observation, a permanent whisper of chaos beneath the apparent calm of the cosmic stage. The quantum foam churns beneath reality's apparent calm, a hidden foundation we can only theorize, but there is a pull in the cosmos so immense it tugs on entire galaxies, a force we can feel but whose source we cannot see. This is the great attractor, far beyond our local group of galaxies, in the direction of the constellation Centaurus, something with the gravitational pull of tens of thousands of Milky Ways is drawing us and everything around us toward it. We are caught in a cosmic current, moving at over 2 million kilometers per hour toward a point we cannot directly observe. The reason for this blindness is a cruel twist of cosmic geometry. The heart of the Great Attractor lies directly behind the plane of our own Milky Way galaxy. This region of the sky is known to astronomers as the zone of avoidance. It is not empty, but rather choked with the gas, dust, and brilliant stars of our galaxy's central disk. This material creates a dense, glowing fog that completely obscures our optical view of the distant universe beyond, like trying to see a distant mountain range through a blinding blizzard. All our powerful telescopes, from Hubble to the newest giants, stare into a wall of our own creation. We know the pull is there because we can measure its effect. We see thousands of galaxies, including our own, streaming like leaves in a river toward this one point. By mapping these flows, we can deduce the location and staggering mass of whatever is doing the pulling. The leading theory suggests it is not a single, unfathomable object, but an immense concentration of mass known as the Norma supercluster, a dense knot of galaxy clusters and dark matter. Yet the exact core, the true epicenter of this gravitational anomaly, remains hidden. It is a mystery literally hiding in our blind spot. We are being summoned by a siren we cannot see, pulled toward a destination whose details are forever veiled by the very stars that light our own night sky. This makes the Great Attractor's core one of the most profound examples of a cosmic region defined by our own perspective. A reminder that sometimes the greatest secrets are hidden not in the distant void, but in the glare of what is closest to us. While the Great Attractor pulls us toward an unseen mass, another colossal force much closer to home holds secrets crushed into impossible forms. Jupiter is not merely a striped ball of gas in our sky. It is a world without a surface, a descent into a hellscape of pressure that transforms familiar matter into alien states. To fall into Jupiter is to embark on a one-way journey through layers of violence. The first clouds of ammonia ice are bitterly cold, whipped by supersonic winds that have raged for billions of years. As you sink deeper, the clear, cold hydrogen atmosphere gives way to a perpetual planet-wide thunderstorm. Pressures mount to thousands of times that of Earth's sea level. The sky, once a pale ochre, darkens to a deep, bruised crimson. Temperatures soar to thousands of degrees, hot enough to melt iron. Here, the very nature of hydrogen, the simplest and most common element in the universe, undergoes a radical transformation. Under the immense weight of the overlying atmosphere, the gas is squeezed so violently that its electrons are stripped away from their atoms. What was once a light, insulating gas becomes a fluid that can conduct electricity as well as any metal. This is metallic hydrogen, a theoretical state of matter that can only exist under pressures exceeding those at the center of our own planet. It is a shimmering, liquid sea of protons and free-flowing electrons, a form of matter we have never been able to create and sustain in a laboratory. This exotic ocean likely generates Jupiter's monstrous magnetic field, a bubble of radiation so intense it would fry the electronics of any spacecraft that dared approach too closely. But the descent does not end there. Deeper still, pressures climb to millions of atmospheres. The core of Jupiter, the seed around which this giant accreted, lies somewhere in that abyss. And what is it? We simply do not know. The original rocky or icy body that acted as Jupiter's anchor may still exist as a compact, Earth-sized ball of heavy elements, superheated to tens of thousands of degrees. Or the relentless pressure and temperature may have dissolved it entirely, its materials mixing into the surrounding metallic hydrogen soup like salt in a boiling ocean. Some models even suggest the core is a fuzzy, diluted region gradually eroding over billions of years. Our best clues come from subtle gravitational tugs on our orbiting probes, but the data is frustratingly ambiguous. This makes Jupiter's deep interior a high-pressure laboratory for physics we cannot replicate, a place where the rules of chemistry and material science are rewritten by sheer force. Any probe we send is doomed long before it reaches these depths. The Galileo mission's atmospheric probe was crushed, melted, and vaporized after surviving for only about an hour, having penetrated less than 1% of Jupiter's radius. To reach the metallic hydrogen layer, let alone the mysterious core, we would need a vessel built from materials that do not exist, capable of withstanding pressures that turn diamond into a paste. Jupiter, the king of our solar system, is therefore a giant vault. Its swirling cloud tops are a brilliant facade, hiding a realm of exotic matter and a lost planetary genesis story we can only guess at. A reminder that some of the universe's most profound experiments are running continuously in the pressure cookers of gas giants, forever beyond our direct inspection. Jupiter's crushing heart is a monument to pressure, but the universe also carves out monuments to its opposite, to profound and staggering absence. These are the cosmic voids, the empty deserts between the great walls and filaments of the galactic web. If the universe's structure resembles a sponge, the voids are the holes, each one a region of space spanning hundreds of millions of light years that contains almost nothing. While the filaments are glittering metropolises of galaxies, the voids are the ultimate ghost towns, dominated not by matter but by the repulsive force of dark energy itself. To find yourself adrift in the center of such a void would be to experience a solitude so complete it defies human comprehension. You would look out in every direction and see almost nothing. The sky would not be a tapestry of stars, but a near-perfect blackness. A handful of lonely, ancient galaxies might dot the expanse, faint smudges of light separated by distances so vast their light would be a pale ghost of its former self. The Milky Way, with its hundreds of billions of stars, would be an unimaginably distant memory. This emptiness is not passive. The void's incredible lack of density means the gravitational pull of matter is negligible here. Instead, dark energy, the mysterious force accelerating the universe's expansion, finds its greatest influence. Within these voids, the very fabric of space itself stretches faster, pushing the scant matter within them ever farther apart, making the void grow even emptier over cosmic time. This creates a fundamental observational paradox. We map these voids from the outside, from our privileged position in a galaxy-rich filament. We can trace their outlines by the absence of light, like charting a canyon by the mountains that surround it. But we can never truly know the interior experience. Any probe sent into a void would, over millions of years of travel, find itself increasingly isolated, its signals fading into the growing silence as the space between it and us expands at an ever-increasing rate. The void is not a place you visit and return from. It is a one-way journey into the universe's expanding silence. These regions represent the ultimate negation, a frontier defined by what is not there, making them some of the most haunting and conceptually challenging deserts in all of existence. Void spaces represent the ultimate emptiness, but some corners of the cosmos are defined by a force of overwhelming presence. Magnetars are the universe's ultimate electromagnets, neutron stars that have undergone a catastrophic transformation. While a typical neutron star boasts a magnetic field 1 trillion times stronger than Earth's, a magnetar's field is another 1,000 times more powerful. This creates a magnetosphere, the region dominated by its magnetic influence, that is not merely a barrier but a realm of physics turned up to a lethal extreme. Imagine a magnetic field so intense it warps the very vacuum of space itself. Within this zone, the concept of a normal atom becomes absurd. The field's power stretches the electron cloud surrounding an atomic nucleus into an impossibly long, needle-thin cigar shape. Atoms cannot maintain their spherical integrity. They are forcibly aligned and deformed by the magnetic torrent, rendering chemistry as we know it impossible. The environment is so distorted it affects light passing through. A phenomenon called vacuum birefringence occurs where the empty space itself acts like a crystal, splitting light rays into two polarized beams. This is a pure quantum effect, predicted but nearly impossible to observe anywhere else in the universe, made manifest on a stellar scale here. For any physical object approaching a magnetar's magnetosphere would be a death sentence of unimaginable precision. Long before you reach the star's surface, the magnetic field would begin to work on you. It would not just crush or pull, it would manipulate matter at the most fundamental level. The magnetic force would be so strong it could overcome the chemical bonds holding your molecules together. A spacecraft or any form of matter would be systematically dissected, its atoms stretched and pulled apart in alignment with the field lines. It would be a disintegration not by explosion, but by magnetic unraveling, a quiet dissolution into a stream of subatomic particles. Furthermore, the energy stored in this twisted magnetic field occasionally releases in cataclysmic starquakes. When the magnetar's rigid crust cracks under immense strain, it unleashes a burst of gamma rays and X-rays that can be detected across the galaxy, momentarily outshining every other source in the sky. These events are a stark reminder of the violent energy pent up in this magnetic prison. We study magnetars from the safety of thousands of light years away, captivated by their flashes and their mind-bending physics. But their immediate surroundings, those seething domains of distorted atoms and twisted light, stand as monuments to forces so fundamentally hostile that they erase the possibility of structure itself. They are cosmic laboratories demonstrating the most extreme consequences of magnetism, experiments we can only observe from the furthest possible distance. Magnetars demonstrate a universe of violent, concentrated power, but the ultimate fate of all things lies in a chilling dissipation of that energy across an infinite, expanding stage. Our journey now leaps across a timescale so vast it defies human intuition to the far future of the universe itself. This is not a place we can travel to, but a temporal destination, an epoch written into the equations of cosmology. Picture a cosmos where the final lights have gone out. Trillions of years from now, the last generation of stars, small, miserly red dwarfs, will have finally exhausted their nuclear fuel, fading into cold, dark embers. Galaxies, now robbed of the gravitational glue of dark matter as they drift ever farther apart, will be mere ghostly remnants, their stars scattered into the deepening void like dust in an endless wind. This is the scenario known as the heat death. In this state, the universe achieves a profound and permanent equilibrium. No more temperature differences exist to drive any process, no stars to create hotspots, no cosmic engines of any kind. The entire cosmos will have cooled to a fraction of a degree above absolute zero, a uniform, thin sea of leftover photons and elementary particles so spread out they might never encounter another again. It is the ultimate silence, the final state of maximum entropy where nothing happens and nothing ever will again. Time itself may become meaningless in such a uniform expanse. Yet there is a more violent alternative finale, one dictated by the mysterious force of dark energy. If dark energy's repulsive strength increases over time, a far more dramatic end awaits the Big Rip. In this scenario, the accelerating expansion of space does not just separate galaxies, it overwhelms every binding force in nature one by one. First, galactic clusters are torn asunder. Then, individual galaxies are shredded, their stars flung into the void. As the acceleration crescendos, the expansion force reaches into solar systems, pulling planets from their stars. In the final, horrific moments, the force invades planets themselves, then molecules, then atoms, and finally the very fabric of space-time. Every structure, down to the subatomic level, is ripped apart in a final, instantaneous flash. Both of these destinies, the slow freeze of heat death or the violent rupture of the Big Rip, are temporal regions we are barred from witnessing. They are the final paragraphs of the cosmic story, conclusions we can project through our models but can never experience. They represent the ultimate frontier of time, a reminder that the universe itself has an expiration date, and our vibrant era of stars and galaxies is but a fleeting, brilliant spark in an unimaginably long and darkening night. The heat death or the Big Rip are conclusions written in the equations of cosmic fate, but the universe's opening act holds a mystery even more profound. In the first trillionth of a trillionth of a trillionth of a second after the Big Bang, something impossible happened. The entire cosmos, smaller than a single proton, underwent a growth spurt of unimaginable violence. This was the inflationary epoch, a period when space itself expanded faster than the speed of light, stretching the embryonic universe by a factor of at least 10 to the 26th power in less than the blink of a quantum instant. To grasp this, picture a single atom suddenly inflating to the size of our entire observable universe, all in a time so short it has no meaningful comparison in human experience. This hyper-expansion was not powered by an explosion into nothingness, but by a bizarre state of energy that permeated the vacuum of space itself. Theorists call this the inflaton field, a kind of cosmic fuel that drove this exponential growth. As this field decayed, its immense energy flooded the universe, heating it into the searing plasma of particles that would eventually become everything we see. This single, fleeting moment solved many of the cosmos's great puzzles. It explains why the universe is so remarkably uniform in all directions, because it all sprang from a tiny, homogeneous region stretched to cosmic scales. It explains why the geometry of space appears so flat, because inflation smoothed out any initial curvature like stretching a wrinkled rubber sheet. Most importantly, it planted the seeds for all future structure. The quantum fluctuations that were microscopic ripples in that inflaton field were stretched to astronomical sizes during inflation. These ripples in energy became the slight variations in density that, over billions of years, gravity would sculpt into galaxies, stars, and planets. We are literally the grown-up children of those quantum whispers, yet, for an event that shaped the entire cosmic landscape, the inflationary epoch is a region forever barred from our direct view. It happened before the universe became transparent, lost behind the wall of the cosmic microwave background's glow. We cannot see it, but we hunt for its fingerprints. Our most promising clue lies in the polarization of that ancient light. As gravitational waves from the violent throes of inflation rippled through the primordial plasma, they would have left a distinct, swirling pattern in the polarization of the cosmic microwave background, a signature known as B mode. Finding this signal is like trying to detect the faintest echo of the universe's first cry. Several ambitious experiments have searched for it, but the signal remains elusive, buried under cosmic dust and foreground interference. This makes the inflationary epoch a foundational ghost. It is the ultimate set designer, arranging the stage upon which every subsequent cosmic drama would play out, yet it vanished before the curtain rose. We live in the aftermath of that incredible event, in a universe whose size, shape, and structure were determined in a fraction of a moment we can only reconstruct through theoretical deduction and relentless, indirect detective work. The inflationary epoch set the stage for every star, but the one that lights our world holds mysteries in its very atmosphere. The sun's outer layers, the chromosphere and corona, are a violent frontier we can never truly touch. We see them as a delicate halo during a total solar eclipse, a shimmering crown of pearly light against the blackened moon. This serene appearance is a beautiful lie. The chromosphere, a thin layer just above the sun's visible surface, is a forest of plasma jets called spicules. These are colossal fountains of superheated gas, each one taller than the Earth, that erupt and collapse in a chaotic dance lasting mere minutes. They are like millions of geysers constantly reshaping a fiery landscape, a dynamic process we can observe but not directly sample. Above this lies the corona, the sun's extended outer atmosphere. Here we encounter one of solar physics' greatest puzzles, the coronal heating problem. The Sun's visible surface, the photosphere, is around 5,500 degrees Celsius. Yet, as you move outward into the corona, the temperature soars to over 1 million degrees. It defies common sense, like walking away from a fire and suddenly stepping into an inferno. The energy to create this multi-million-degree oven is thought to come from the Sun's tangled magnetic fields, which snap and reconnect in a process that violently heats the plasma, but the precise mechanism remains just out of our grasp. This superheated corona is not a placid cloud. It is the birthplace of solar weather. When those magnetic field lines become too twisted, they can explosively realign in a solar flare, releasing in moments the energy of billions of atomic bombs. Even more consequential are coronal mass ejections, where billions of tons of charged plasma are hurled into space at millions of kilometers per hour. These events sculpt the space around our planet, creating the dazzling auroras, but also posing a severe threat to satellites, power grids, and astronauts. To understand these storms at their source, we would need to send a probe directly into this maelstrom, but the environment is one of utter annihilation. The radiation flux would instantly fry any electronics not shielded by impossibly thick barriers. The particle bombardment from the solar wind, a constant supersonic stream flowing from the corona, would erode any physical structure like sandblasting at an atomic level. And the sheer heat would vaporize any known material. Our most daring missions, like the Parker Solar Probe, are engineering marvels that dip into the corona's outermost fringes, protected by a revolutionary heat shield. But they cannot survive a journey to the heart of these phenomena. They are like sending a weather balloon into the outer bands of a hurricane, giving us invaluable data about the storm's edges, while the furious, churning eye remains an unreachable mystery. The Sun's crown, therefore, is a region of breathtaking violence and profound scientific questions, a cosmic engine whose inner workings we must decipher from a safe and permanent distance. The Sun's violent atmosphere is a realm of fire we cannot touch, but a far colder and darker mystery may be circling our own solar system, a ghost in the gravitational machine. For years, astronomers studying the outer solar system have noticed something strange. A collection of small, icy objects beyond Neptune, called trans-Neptunian objects, share a peculiar orbital alignment. Their elongated paths are clustered together in a way that should not happen by random chance. It is as if an unseen shepherd, a massive gravitational hand, is herding them into this strange configuration. The most compelling explanation is a world we have never seen, a hypothetical giant known as Planet 9. This is not a small, rocky body, but a potential ice giant with a mass up to 10 times that of Earth, a true major planet lurking in the perpetual twilight. Its proposed orbit is a lesson in cosmic scale and isolation. Unlike the near-circular paths of the known planets, Planet 9's orbit would be a long, skinny ellipse, a cosmic racetrack stretched to an extreme. At its closest approach to the Sun, it might still be several times farther out than Neptune, but at its most distant, it would venture into the deep freeze, perhaps 20 times farther than that, a lonely voyage into the Sun's weakest grip. One single orbit along this immense path could take between 10 and 20,000 years to complete. From the perspective of human civilization, a planet like this moves with glacial slowness, inching across the sky over centuries. This combination of extreme distance, incredible faintness, and sluggish motion is what has kept it hidden from our most powerful telescopes. Finding it is like searching for a single, dim coal in a vast black field and not knowing exactly which field to look in. Its realm is the frozen outer darkness, a place where the Sun is just a particularly bright star and temperatures hover near absolute zero. Any mission to reach it would be a voyage for the ages. Even with our fastest propulsion, a spacecraft would take decades, perhaps centuries, just to arrive. It would be a generational endeavor, a project begun by one generation with the hope that their great-great-grandchildren might see the first blurry images. Planet 9, therefore, represents a different kind of sealed region. It is not barred by fire or crushing pressure, but by the sheer, silent vastness of our own cosmic backyard. It is a potential member of our planetary family, a giant world whose existence is written not in light, but in the subtle gravitational whispers of distant ice. We feel its pull on the tiny dancers at the edge of our system, yet the dancer itself remains a silhouette, a haunting possibility that our solar system is still holding its greatest secret in the dark. The gravitational whispers of Planet 9 hint at unseen giants, but mathematics allows for far stranger creatures lurking in the equations of relativity. If black holes are cosmic drains, then white holes are their theoretical opposite, impossible fountains. They appear as valid solutions in Einstein's field equations, the same mathematics that predicts black holes and the bending of starlight. A white hole would be a region of space-time where matter and energy can only spew outward, never be entered. It is the time reversal of a black hole's relentless pull, a cosmic geyser erupting with the force of a singularity. Imagine trying to paddle a canoe up the outflow of the most powerful waterfall in existence, a torrent moving at the speed of light. That is the futile task of approaching a white hole's event horizon. Its boundary is not a point of no return, but a point of no approach. Any matter or radiation, any probe or particle, would be violently repelled by the sheer force of the outward explosion. The closer you got, the more intense the blast would become, a wall of pure energy pushing you back into the void. This makes the event horizon of a white hole, if such a thing could exist, a one-way surface in reverse, a door that only opens outward. Physicists largely consider white holes to be mathematical curiosities rather than physical realities. The reason is profound instability. Our universe is governed by a relentless increase in entropy, a trend toward disorder. A white hole, which would spontaneously generate ordered energy from a singularity, seems to violate this most fundamental arrow of time. Any perturbation, any stray bit of matter falling toward it, would theoretically collapse the entire delicate structure back into a black hole. They are like perfect inverted castles made of mathematical sand, beautiful to contemplate but washed away by the slightest tide of reality. So while we can write them into our theories, the universe appears to have no place for such permanent outbursts. They remain ghostly reflections in the mirror of relativity, reminding us that not everything mathematics permits, nature allows. White holes are cosmic fictions, but the vast spaces they might inhabit are very real. Beyond the sparse deserts of cosmic voids lies an even more pervasive emptiness, the deep intergalactic medium. This is not the space inside galaxies sparkling with stars, nor is it the relative emptiness of a void. This is the foundational ocean, the thin, hot gas that fills the colossal volumes between all galactic structures, the background hum of the universe's ordinary matter. While it contains more total atoms than all the stars and galaxies combined, its distribution is so incredibly diffuse it defies human senses. Picture a single, lonely hydrogen atom adrift in a volume of space the size of a child's bedroom. That is the typical density of the deep intergalactic medium. For comparison, the air we breathe packs about 25 billion molecules into that same space. This medium is not cold and dark, however. It is ionized, meaning its hydrogen atoms have been stripped of their electrons by the fierce ultraviolet light from the first galaxies and quasars, heated to temperatures of hundreds of thousands of degrees. It is a scorching, invisible fog, a plasma so thin it would feel like a perfect vacuum to any physical object passing through. Mapping this ghostly ocean is one of astronomy's greatest challenges. We cannot see it directly, for it emits almost no light of its own. Instead, we study it by observing the most brilliant beacons in the distant cosmos, quasars. As the intense light from a quasar billions of light years away journeys toward us, it passes through countless filaments of this intergalactic gas, Specific wavelengths of that light are absorbed by the atoms within the gas, leaving dark lines in the quasar spectrum like a cosmic barcode. By analyzing the patterns of these absorption lines, astronomers can deduce the composition, temperature, and distribution of the gas along that single, needle-thin line of sight. It is a painstaking process, like trying to map the structure of a fog bank by studying how it dims the headlights of a single, distant car. This method reveals the medium is not uniform. It is woven into a vast cosmic web, with denser filaments tracing the same structures as galaxies and voids, and enormous, billowing bubbles blown by the galactic winds of ancient starbursts. To be adrift in the deep intergalactic medium would be to experience the ultimate solitude. Your ship would be surrounded by a near-perfect vacuum, yet one that is paradoxically hot enough to vaporize steel, if only there were enough particles to conduct the heat. There would be no up or down, no landmark in any direction. The nearest galaxy would be a faint, hazy smudge so distant that millions of years of travel would not bring it noticeably closer. You would be floating in the universe's baseline state, a silent, immense ocean where the very atoms are too far apart to ever touch. We sample this realm only through the most delicate forensic techniques, interpreting the shadows it casts on light from impossibly far away. It is the connective tissue of the cosmos, the space between all places, and yet it remains a region we can only ever know in theory, a fundamental component of reality forever out of physical reach. The deep intergalactic medium is a ghostly ocean of near-nothingness, but there are objects that defy the simple categories of planet or star, hiding their own internal strangeness. Brown dwarfs are the cosmic in-betweeners, often called failed stars. They form like stars from collapsing clouds of gas, but they simply lack the necessary mass to ignite the sustained nuclear fusion that powers a true star. They are too heavy to be considered gas giants, yet too light to shine with their own fiery light. This ambiguous identity makes their interiors a mystery sealed by gravity and extreme pressure. Imagine a world where the sky is not a gentle blue but a perpetual broiling twilight, lit only by the dull red glow of residual heat from its violent birth. The atmosphere of a brown dwarf is a bizarre laboratory. As you descend, you would encounter clouds unlike any in our solar system. Instead of water vapor or ammonia, the skies might be filled with droplets of molten iron or silicates falling as a scorching rain of liquid rock. Further down, you could find clouds of hot sand, tiny grains of minerals condensing out of the searing, turbulent air. These are not placid, Earth-like weather patterns, but global tempests in an atmosphere thousands of degrees hot, driven by internal heat slowly leaking away over billions of years. But the true enigma lies deeper beneath these alien skies. The interior of a brown dwarf is a layered onion of exotic matter, a structure we can only model. At the upper layers, immense pressure squeezes hydrogen gas into a fluid form of molecular hydrogen. Deeper still, the pressure becomes so catastrophic that the molecules themselves are torn apart. The electrons are stripped from their atoms, creating that bizarre sea of metallic hydrogen we suspect exists within Jupiter, but here it forms a vast, deep ocean. And at the very core, conditions might become so extreme that helium, which normally remains a gas, could separate out and condense into droplets, falling through the denser hydrogen like a slow-motion rain of liquid helium, a phenomenon literally called helium rain. This internal architecture is not static. As the brown dwarf cools over its immense lifetime, these layers likely shift and evolve, with different compounds condensing out of the atmosphere and sinking, driving complex, unseen weather deep within. We study brown dwarfs by the faint infrared glow of their cooling embers, and we can analyze the chemical fingerprints in their light, but these are surface hints. We have no way to probe the internal dynamics, to sample the metallic hydrogen ocean, or to witness the helium precipitation. They are cosmic hybrids holding the secrets of how gas giants transition into stars, yet their hearts remain forever inaccessible, making each one a locked chest floating in the dark, its contents inferred but never seen. The emptiness between galaxies is not uniform, but in one particular direction, it swells into a staggering abyss of nothingness. This is the Boötes void, a spherical region of space so profoundly empty it challenges our very models of the cosmos. At 330 million light-years across, it is not merely a gap, it is a cavern. If you placed our Milky Way at its center, you would have to travel for tens of millions of years at light speed in any direction before encountering another galaxy. For scale, the entire local group of galaxies we belong to would fit inside this void over 7,000 times. Within this colossal volume, astronomers have found only about 60 galaxies. In a similarly sized region of the typical cosmic web, you would expect to find 10,000. The Boötes void is not just empty, it is unnaturally, suspiciously empty. Its existence pushes at the limits of what our standard model of cosmology, with its random quantum seeds from inflation, can easily explain. How could a structure this large form with so little inside it? One theory suggests it is not a single void, but a cosmic accident, the merger of several smaller voids that happen to align, their emptiness combining into one supervoid. It is like several soap bubbles in a sink randomly coalescing into one giant, fragile sphere of nothing. Another, more speculative idea wonders if something more exotic occurred in that region long ago. Could some unknown repulsive force, an early and localized burst of dark energy, have pushed matter out? Or was it the site of a titanic, pre-galactic conflict where the gravitational tug of war between nascent superclusters left this vast no-man's land behind? We may never know the cause, but we can contemplate the experience. To be inside the Boötes void would be to witness the ultimate dark sky. You would float in a blackness so complete it feels solid. The few, faint galaxies present would be lonely, reddish pinpricks, their light stretched by the void's expansion, offering no sense of home or structure. There would be no galactic horizon, no misty band of the Milky Way, just an endless, starless night in every direction, a solitude so vast it would feel like being the last conscious thing in existence. This specific, named void is a monument to the universe's capacity for absence, a grand-scale mystery carved into the fabric of space itself, reminding us that even nothingness can take on forms of breathtaking scale. The Boötes void is a cathedral of cosmic absence, but within the furnace of a star, every cubic centimeter is a riot of creation. At the heart of our sun, beneath hundreds of thousands of kilometers of churning plasma, lies a continuous thermonuclear explosion. This core is a place of almost incomprehensible extremes. The temperature soars to over 15 million degrees Celsius, and the pressure is more than 250 billion times what we feel at sea level on Earth. Here, hydrogen nuclei, which are single protons, are squeezed together with such force that they overcome their natural electromagnetic repulsion, a force that normally makes positively charged particles violently push each other apart. They fuse, creating helium and releasing the energy that has lit our world for 4.6 billion years. This process is the ultimate alchemy, transforming the simplest element into the building blocks for everything else. But the secret of how this happens is not just brute force, it is a delicate quantum mechanical ballet. The protons in that searing plasma do not actually have enough classical energy to smash through their mutual repulsive barrier. They cheat, they utilize a bizarre quantum effect called tunneling. Imagine two balls rolling toward each other up a steep hill. Classically, if they don't have enough speed to reach the top, they will roll back. In the quantum world, there is a tiny but real probability that one ball will simply appear on the other side of the hill without ever going over the top. It tunnels through the energy barrier. In the solar core, this tunneling probability is what allows protons to get close enough for the strong nuclear force, which only works at incredibly short ranges to snap them together. This means the heart of our sun is not just a place of physics we know, but a domain ruled by probability and uncertainty. We can write the equations for these reactions. We can simulate them in supercomputers and even create fleeting fusion in laboratories. But the true, chaotic environment of a stellar core is a realm we can never directly sample or witness. It is a maelstrom of nuclei colliding, tunneling, and fusing in a probabilistic dance, a quantum riot shielded from us by the star's own brilliant body. We see the glorious light that results, but the furious, foundational engine remains a hidden inferno, a place where the mathematics of the very small powers the radiance of the very large. Our journey has taken us to places where the laws of physics are bent, broken, or simply absent. But there is one theoretical monster so unsettling that physicists have proposed a universal law just to keep it locked away. This is the naked singularity, and the region just outside it would be a frontier of true cosmic chaos. The cosmic censorship hypothesis, first proposed by Roger Penrose, is essentially a hopeful plea for order. It suggests that nature abhors a bare singularity. Whenever a star collapses or matter becomes too dense, the forces of gravity will always wrap the resulting point of infinite density, the singularity, inside an event horizon, hiding it from the rest of the universe. This horizon acts as a protective curtain, shielding the predictable cosmos outside from the infinite, lawless weirdness within. A naked singularity would be a violation of this cosmic decorum. It would be a singularity without its protective event horizon, a point of infinite density and curvature exposed for the entire universe to see. Think of it as a tear in the fabric of reality, left gaping open. The immediate vicinity of such an object would not be a place of orderly orbits or predictable forces. It would be a maelstrom of unpredictable spacetime geometry. The equations of general relativity, which normally allow us to calculate the path of planets and the bending of starlight with exquisite precision, would simply break down. You could not plot a safe course or predict what would happen from one moment to the next. Causality itself, the principle that cause must always precede effect, could be thrown into disarray. Time might loop back on itself, or space could twist into knots that change faster than any computer could calculate. It would be a zone where the universe's rulebook is not just rewritten but shredded. The debate over whether naked singularities can actually form is fierce. Some complex mathematical models of rotating black holes or collapsing exotic matter suggest it might be possible to shed the event horizon like a snake shedding its skin, leaving the singularity exposed. Others argue that some unknown quantum gravitational process will always step in at the last moment to preserve cosmic censorship, like a universal safety mechanism. But if a naked singularity did exist, its event horizon, or rather the space where that horizon should be, would be the most treacherous non-boundary imaginable. There is no point of no return to warn you. You would simply be sailing into a storm of pure unpredictability. One moment, the geometry of space might be gently curved, guiding you in a wide arc. The next, a violent spike in curvature could spaghettify your ship without warning. The very fabric of cause and effect could unravel around you, making the concept of exploration meaningless. How do you explore a place where the outcome of your actions cannot be known? This makes the environs of a naked singularity the ultimate no-go zone, not because it is hidden behind an impenetrable wall, but because it is a visible wound in reality where physics as we know it ceases to function. It is a reminder that the universe's most profound secrets might be guarded not by distance or density, but by the very requirement for a predictable, orderly reality in which science can even be done. While naked singularities threaten the very laws of cause and effect, the universe also constructs monuments of such immense scale they defy another fundamental principle, the idea that the cosmos should look roughly the same in every direction. This is the Hercules Corona Borealis Great Wall, a filament of galaxies so vast it strains our understanding of cosmic structure, stretching an almost incomprehensible 10 billion light-years from end to end. It is one of the largest single things we have ever identified. To grasp its scale, if you could travel at the speed of light, it would take you twice the entire age of the Earth just to cross it. This is not merely a cluster of galaxies, it is a continent of them, a sprawling metropolis of galactic superclusters bound together by gravity into a single, thread-like structure. Its discovery presented cosmologists with a profound puzzle. A cornerstone of modern cosmology is the cosmological principle, which states that on the largest scales, the universe should be homogeneous and isotropic, essentially smooth and without a preferred direction. The Great Wall, with its staggering concentration of matter spanning a significant fraction of the observable universe, appears to be a glaring exception. It is a feature so immense it makes us question if our view of the cosmic web is complete, or if we are simply seeing the largest thread in a tapestry whose full pattern we cannot perceive. Our understanding of this Leviathan is fundamentally limited by our perspective in both space and time. When we look at the Hercules Corona Borealis Great Wall, we are not seeing it as it is now. We are seeing it as it was billions of years ago, a fossilized snapshot of its younger self. The light from its most distant galaxies has been traveling for over 10 billion years to reach us. Furthermore, we see it as a two-dimensional smear across our sky. We can map its position and infer its distance, but comprehending its true three-dimensional architecture, its twists, its voids, its internal bridges and knots, is like trying to map a mountain range by studying its shadow on a distant wall. We cannot know its true shape or its current gravitational influence. Is it still a coherent structure, or has the accelerating expansion of the universe begun to tear this cosmic continent apart? We have no way to know. It exists for us as a ghostly imprint on ancient light, a reminder that the largest structures in existence are also the most elusive, their true nature forever flattened and frozen by the very light that reveals them. These 25 sealed chapters, from the singularity's infinite pinch to the Boötes void's staggering emptiness, share a single, humbling truth. The universe is not a museum designed for our visitation. It is a wilderness of wonders whose most profound exhibits are forever locked behind glass we cannot break. Glass made of impossible distances, annihilating physics, or the irreversible flow of time itself. We have mapped the edges of these realms with mathematics and inference, listening for their gravitational echoes and studying the shadows they cast. Yet the true nature of the quantum foam, the heart of a neutron star, or the ocean floor of Europa remain as distant to our hands as they are close to our curiosity. This is not a failure of science, but its very engine. Each of these cosmic no-go zones represents a screaming question written into the fabric of reality. They are the ultimate puzzles, driving us to refine our theories, build better telescopes, and imagine more wildly than ever before. They remind us that wonder is not conquered by arrival, but sustained by the journey toward understanding. Our reach will always exceed our grasp, and in that beautiful, frustrating gap lies the endless pursuit of knowledge. So tell me, which of these forbidden frontiers captures your imagination the most? Is it the hidden ocean of a rogue planet, or the chaotic doorstep of a naked singularity? Let the conversation continue below. And if you hunger for more journeys to the edge of understanding, make sure to subscribe. Our exploration of the cosmos's greatest mysteries has only just begun.